Hello students, I will continue with a small part from the last week and then I will start the topic for this week. So we continue with one example. In this example, a load of 5000 Newton resulted in a static displacement of 0.05 meter in a composite structure. A harmonic force of amplitude 1000 Newton is found to cause a resonant amplitude of 0.1 meter. Find part A, the hysteresis damping constant of the structure. Part B, the energy dissipated per cycle at resonance, and the steady state amplitude of at 1/4 of the resonant frequency. We can find the stiffness of the system because we have the weight, we have the static deflection, so we can find the stiffness of the system. And also we can find by using the equation for the amplitude of the response in resonance, we can find the hysteresis damping constant, which is 0.1. In part B, the energy dissipated per cycle at resonance, which is equal to pi times by the equivalent viscous damping constant times by omega, which omega is the frequency of the excitation, and multiplied by uppercase x squared, which is uppercase x is the amplitude of the response. So we can find the energy dissipated in each cycle, and finally the steady state amplitude at 1/4 of the resonant frequency. It means that the frequency ratio must be 1/4 or 0.25. So we can substitute for this frequency ratio and obtain the amplitude of the response. The next concept is the self-excitation and stability analysis. Self-excited systems is a phenomenon that sometimes happen in the practical systems when the exciting force is a function of the motion. In fact, the equation of motion, when you derive the equation of motion, you will see that the terms x dot, but the coefficient of x dot is not related to the damping. And in fact, this is the exciting force, which is a function of the velocity, and it will happen in some systems, for example, in a rotating shaft, in a flutter of turbine blades, in a flow induced vibration of pipes, and a lot of other examples. When you extract the equation of motion, you will see that we have the terms of the velocity, but the coefficient of this velocity is not damping, and this term will create some positive energy, and it will insert some energy into the system, which cause the instability in our system. So we define the dynamic stability, which is similar to the definition for the stability or stable system. A system is dynamically stable if the motion converges or remains steady with time. You can see the definition of dynamic stability is similar to the stable system, and also the motion diverges and the system becomes unstable if the energy is fed into the system through self-excitation. So the self-excitation always causes the instability in the whole system, because as I told you, the term x dot in the equation of motion, when you solve the equation of motion, it will affect as a singular term on your equation of motion, and when you solve the equation, you will see that we have some terms in the response that will cause to increase the amplitude of the response by time, and the amplitude will not remain the same by time, and it will diverge, and the system will become unstable. If we want to study the dynamic stability in the system by investigating the roots of the characteristic equation, we can assume that the roots of the characteristic equations are alpha 1 and alpha 2. If you remember, when you form the characteristic equation, it was the form of m alpha squared plus b alpha plus c alpha plus k, which m was the coefficient of x double dot in the equation of motion, c was the coefficient of x dot, and k was the coefficient of x in the equation of motion. So we have an algebraic equation, and you can solve this equation using the delta method. The roots of this equation, we call them alpha 1 and alpha 2, and we assume that alpha 1 and alpha 2 are in the general form of p plus minus iq, which p is the real part and q is the imaginary part of the roots. And you can see this is the complex conjugate roots. So now we want to discuss the effect of the sign for p and q on the stability of the system. So if we substitute into the characteristic equations, we can rewrite the characteristic equation in this form, because we know that the roots of this equation is alpha 1 and alpha 2. I mean the equation m alpha squared plus c alpha plus k is equal to 0. This is the characteristic equation. And now we know that the roots of this equation is alpha 1 and alpha 2. So we can rewrite this equation in this form, because we assume that alpha 1 and alpha 2 are the roots of this equation. So we rewrite in this form. Now we can expand this equation and collect for alpha. So we will have alpha squared minus alpha 1 plus alpha 2 times by alpha plus alpha 1 times by alpha 2. So if we compare this equation with the characteristic equation in the initial form, or this equation, in the first equation, we call it equation 1. If you divided equation 1 by m, we will have this equation alpha squared plus c divided by m times by alpha plus k divided by m. Now we can compare these two equations, equation 2 and equation 3. If you compare these two equations, you can conclude that alpha 1 plus alpha 2 is equal to c divided by m, of course with a negative sign, and alpha 1 times by alpha 2 is equal to k divided by m. So because the coefficient of alpha in equation 2 is c divided by m, and the coefficient of alpha in equation 3 is minus alpha 1 plus alpha 2, so these two terms must be equal. And also k divided by m, which is alpha 1 multiplied by alpha 2, are the constant part of two equations 2 and 3. So we can easily conclude that minus alpha 1 plus alpha 2, which is p plus iq plus p minus iq. So plus iq with minus iq will cancel out each other, and we will have the summation of alpha 1 plus alpha 2, which is equal to 2 times by p, and we have one negative, so it will be minus 2 times by p. It must be equal to c divided by m, and also alpha 1 plus by alpha 2. Again, if you substitute, alpha 1 is equal to p plus iq, and alpha 2 is p minus iq, and simplify this, you can conclude that alpha 1 times by alpha 2 is p squared plus q squared. You know that p plus iq multiplied by p minus iq is equal to p squared minus I times by q squared, which I times by q squared is equal to minus q squared, and we have another minus, so it will be positive. So p squared plus q squared must be k divided by m. So here you can see, and according to the sign of p and q, we can conclude that this term must be positive, k divided by m, because p squared is positive and q squared is positive as well. So k divided by m must be positive. It means that k must be positive because m is the mass of the system, so definitely m is positive. So K, the stiffness of the system must be positive for a system with stability. And for the C divided by M, for negative P, it means when P is negative, this term minus 2 times by P will be positive. So C divided by M must be positive. And again, we can conclude because M is a positive value, so C must be positive as well. So C and K must be positive in the system to have a stable, dynamical, stable system. Okay, so by this concept, we can wrap up the topics for week 6, and now I will start the topics for week 7. Okay, this week we start the vibration under general forcing conditions. For this purpose, we study the response under general periodic force and the response under non-periodic forces. So in the real world and in the practical systems, many of the practical systems are subjected to several different types of forcing, which they can be they can have a general form, and usually they are not harmonic. Maybe they can be periodic, but they are not harmonic, or they don't have a harmonic form. So in this type of structures, we will have two different cases. The first case, we can find a periodic function or periodic form for the excitation. Of course, non-harmonic, it's only periodic. So it can be replaced by a summation of different harmonics by using the Fourier series. So first we use the periodic function and Fourier series to find an equivalent definition for the periodic function, to find a summation of different harmonics, and then when we find the harmonic excitation form, we can find the response separately for each harmonic. For example, we can find that the periodic function is a combination of 2 or 3 different harmonics with different frequencies. So the response, or the steady state response in fact, and the particular response is equal to the summation of 2 or 3 different harmonics with the same frequencies. So the response will be similar to the previous section, but only we need to find the harmonic functions for the periodic function by using the Fourier series. And the second case is the non-periodic excitation. In this case, we cannot find a periodic form for the response, and it has a general form. It's not a function, a periodic function. So we can find, of course, in this course, we only use these 3 different methods, but there are some other methods. In this course, we only study the convolution integral method, the Laplace transform, and also we will have an introduction to the numerical methods to find the response of a system to a general excitation. So first start with a system under periodic excitation. When we have the periodic excitation, the function ft, for example, assume that the system is subjected to the external force Ft, which is a periodic with period tau, which tau is equal to 2 pi divided by omega, and omega is the frequency of the period function Ft. So it can be expanded in a Fourier series. We know that any periodic function can be rewritten in the form of a Fourier series as a combination of cosine and sine functions by using this equation ft is equal to a naught divided by 2, which a naught can be obtained using this equation. A naught is equal to 2 over the period multiplied by the integral of ft dt, which ft is our periodic function, plus the summation of a n times by cosine n omega t. So a n is the coefficient of cosine harmonics and bn is the coefficient of sine harmonics with different frequencies. You can see the frequencies start from omega and it will continue with 2 omega, 3 omega, because n is from 1 to infinity. So ft in fact is an infinite series, but we can use a finite number of these harmonics to find an approximation for ft. So this is an approximation solution, but the accuracy of this solution is usually acceptable, and we will discuss that how many number of the terms in this series will be required to find an acceptable estimation for the response. So this is the ft, or the Fourier series of a periodic function ft. The coefficient of cosine harmonics an is equal to 2 divided by tau ft times by cosine n omega t. So you can see that you can solve this integral and obtain that an is a function of n, as you can see. And also for bn, the coefficient of sine harmonics, we can use this equation. And you can see again, if you solve this integral and extract the response, you can see that bn is a function of n again. So finally, ft can be rewritten as a function of the combination of cosine and sine harmonics with different frequency. So if you expand this term, this summation, if you expand this, it will be equal to, for example, a1 times by, instead of n we should substitute 1, so it will be cosine omega t, plus instead of n we substitute 1, so it will be b sub 1 times by sine, once again instead of n we substitute 1, so it will be omega t. So we substitute the next term is n is equal to 2, so it will be a sub 2 times by cosine, this time instead of n we substitute 2, so it will be 2 times by omega t, plus b2 b sub 2 times by sine 2 times by omega t. And the next term, which is plus, this time is a, we should substitute n is equal to 3, so it will be a3 cosine 3 omega t plus b3 sine 3 omega t, and so on. So it will continue, and of course we have a0 divided by 2. I only wrote here the these summation terms. So you can see this is a combination of different frequencies. As you can see here, we have frequency omega. So the particular response for this part is, for example, a cosine omega t plus b sine omega t. So this is the particular response for this part, for the first harmonic. The second harmonic is with frequency 2 omega. So we need another particular response for this part. So it will be plus, for example, it can be c times by cosine 2 times by omega t, plus, for example, d times by sine omega t, and so on. For example, for the third harmonic, it will be A3 cosine 3 omega t. So we consider, for example, E times by cosine 3 omega t plus, for example, F sine 3 omega t. And these coefficients A, B, C, and D can be obtained by substituting into the main equation, and then we can find these constant coefficients in the main equation. So you can see only the different from this part and the section in the previous section when we solve the particular response and obtain the particular response for the harmonic excitation is only to obtain these harmonics. So the first step, you need to find the equivalent harmonics or the Fourier series for ft and this function, and then you can find the particular response here. The particular response is a combination of different frequencies. So this is the total procedure to find the particular response for a system subjected to a periodic excitation. But how many terms in this series we need to find a good estimation or an acceptable estimation for the response? It's up to you. You can study that how many terms give you a coverage response, give you an acceptable response. So you can check the convergence of your response, and also you can plot it. For example, here you can see this is the ft, which is a periodic function. As you can see, the definition for ft is equal to t for t between 0 and 2 pi. So the period of this term, the period of this function is equal to 1. And if you plot ft, you can see it has a periodic form like this. And now if you plot the Fourier series for ft for different number of series, you can see it. For example, when n is equal to 4, I plotted the ft. You can see it's similar to the original function, but still we have some difference between ft and its harmonics. So this is the ft. When we consider here, instead of infinity we substitute 4, so we can achieve a curve something like this. The next one is for n is equal to 40. I mean, next one, I find the response for n is equal to 1 to n is equal to 40. So if you plot the response, you can see we are close to the original function. I mean, only in this area we have some noises, but generally, if you plot and neglect these very small perturbation, you can see that this is an acceptable estimation for the original ft here. And finally, here when we substitute n is equal to 80, I mean here I considered 80 terms in this series. You can see again these perturbations are really small and we can neglect them. So according to your conditions and how much of these perturbations can be acceptable in your work, you can consider the number of the terms in this series. But in this course, in the exam, if I give you any question and if you want to solve using the Fourier series, definitely I will tell you that how many number of the terms you need. So in this course, it's not a challenge for you. You can easily find an and then you can find a1. For example, if I asked you to find the response for 2 terms, so you only need to substitute n is equal to 1 and 2. So easily you can find the response for these 2 harmonics and find the response for the system. subjected to a periodic excitation. Any question? Is it clear? Okay, we can consider a first order system. Here you can see this is a first order system because when you extract the equation of motion, you will see that the governing equation is an ODE from order 1. So we call it first order system. And the reason is because here we don't have any mass. So if you write the equation of motion, we will have cx dot plus kx minus y is equal to 0. Here we don't have any mass, so we don't have any acceleration. So in the right hand side of the Newton's second law, we will have 0 because the mass is 0. So this is the equation of motion. X is the displacement of point B and y is the displacement of point A. So the deflection in the spring is the difference between point A and B, or x minus y. And the force in the damper is the velocity of point B, which is x dot multiplied by the damper constant. And now we can write that the equation of motion is cx dot plus kx is equal to ky. And now we can write, for example, we can assume that the excitation Vy is a periodic, sorry, it's not harmonic, it's only a periodic excitation. So now we can find, using the Fourier series, we can find the harmonic form of this periodic function. So when yt is a periodic function with frequency omega, we can write it in this form, a summation of different harmonics. So we need to find the particular response for this equation. Using the ODE theories, you can find the particular response for these functions, which is a naught divided by 2. This is the constant part because of this term. And this is the sine harmonics, and this part is the cosine harmonics. As you can see, we have the coefficient of sine harmonics as a function of n and omega, and also the coefficient of cosine harmonics as a function of n and omega again. So you can find the particular response by using this Fourier series, and this is a system with order 1. So the first step, we find these coefficients a(n) and bn, and then if you find the particular response according to the ODE theories, you can find these constant coefficients for sine and cosine harmonics. This is the first order system. Okay, we want to, for example, here, we want to determine the response of a system with the equation of motion below. Assume that the initial condition is 0. So here we have one first order equation, x dot plus 1.5x is equal to 7.5. This term is in fact a constant part, plus 4.5 cosine t plus 3 times by sine 5t. You can see the non-homogeneous term includes one constant part. This is the constant part. So we should find one particular response for this part. We call it, for example, xp1. We have one harmonic with frequency 1. So we need to find another particular response for this frequency. We call it, for example, xp2. And finally, we have one harmonic with frequency 5. So we need another particular response, which we call it xp3 for this non-homogeneous term. So the first one, the xp1 for 7.5, we consider that the particular response is a constant value because this is a constant value. So xp1 is a constant value. When you substitute into the main equation, this is the main equation. When you substitute here, the derivative of the constant value, we assume that, for example, xp1 is a constant value c. Now we need to obtain the numerical value for c. We need to substitute xp1 into this main equation. The derivative of a constant value is 0, so it will be 0 plus 1.5 times by xp1, so it will be 1.5 times by xp1, which is c. This is the point. It must be equal to 7.5. So from here we can conclude that c or xp1 is equal to 7.5 divided by 1.5, which is 5. So this is the particular response for the first non-homogeneous term. Now we need to obtain the particular response for the second non-homogeneous term, which is a harmonic with the frequency of 1. So for this equation, we assume that xp2 is equal to, in the general form, of uppercase x2 cosine t minus phi2, which phi2 is the angle phase and x2 is the amplitude. And then we can find x2 and phi2 by substituting into the main equation. So these are phi2 and x2, or you can use the formula that we had for this response. And finally, we need to find a particular response for the last part here, which frequency 5. So for this term, we assume that xp3 is x3 sine 5t minus phi3, which x sub 3 and phi sub 3 are amplitude and the angle phase respectively. Also, another way that you can find the response, the particular response for these equations, you can assume for part 2 here, for xp2, you can consider that, for example, a times by cosine t plus b times by sine t. And a and b, these two coefficients, will be obtained by substituting into this equation. You need to find x dot, substitute. X dot is minus a sine t plus b cosine t. And then you can substitute here, instead of x, you can substitute a cosine t plus b sine t. And then simplify. The coefficient of sine t in the left hand side must be equal to 0, because in the right hand side the coefficient of sine is 0, and the coefficient of cosine must be equal to 4.5. So this is another method. And also for this one, xp3, again you can consider that the particular response is equal to a times by cosine, this time is the frequency is 5, so it will be cosine 5t plus b times by sine 5. So you can see, again, a and b can be obtained by substituting into the main equation. Again, x dot is minus 5 times by a times by sine 5t plus 5 times by b times by cosine 5t. And then you substitute here, instead of x, you can substitute this term. And then simplify. Again, the coefficient of sine 5t in the left hand side must be equal to 0, because in the right hand side here we only have cosine function and the coefficient of sine function is 0. The coefficient of cosine function in the left hand side must be equal to 3. And finally you can find a and b, or again you can use these two formula to obtain the amplitude and angle phase. And finally, the particular response for this equation is equal to xp1 plus xp2 plus xp3. According to the superposition principle, you can find a particular response or the steady state response for this equation. Is it clear? Any question? Okay. Finally, we can consider a second order system. It means that the governing equation will be a ODE from order 2. Here we have a system, a simple single degree of freedom system with mass m, stiffness k, and damping constant c. Ft is a periodic force, so we can write Ft in the form of combination of different harmonics. As you can see, we can write Ft by using its uh, Fourier series definition. We can write in this form. Here, instead of n, I used j. In fact, this is an. Instead of n, we have j, which j varies from 1 to infinity. And we can find a particular response. Here you can see we have different harmonics. It starts from 1, so we will have first a harmonic with frequency omega, then harmonics with frequency 2 omega, harmonics with frequency 3 omega, and so on. So we can find a particular response similar to the excitation, which is a combination of different harmonics. We can find a particular response as a combination of different harmonics with different frequencies from omega to omega, 3 omega, and so on. So if you use the formula, you can write that xpt by using the principle of superposition. You can write that the particular response is a combination of different frequencies. As you can see, it starts from j. When j is equal to 1, its frequency is omega. When j is 2 omega, and so on. And also the coefficient can be obtained by using the definition of aj and bj. So once you obtain aj and bj, you can substitute here and find the particular response, and also the angle phase for each harmonic, which is obtained again as a function of j, and also the frequency ratio and damping ratio. So you can obtain the particular response for a system from order 2 by using these equations, these definitions, and find the particular response for a system subjected to a periodic excitation. Okay, any question? If you don't have any question, we can wrap up this session and continue on Wednesday. Okay, thank you for your attention, and we continue on Wednesday. And